In this video, we're going to look at doing the independent t-test, and we're going to be trying to answer the question, is there a difference in the birth weight of babies who are born to mothers who have ever smoked versus those who have never smoked? Now, there are actually 4 categories of smoking in this data set. Never smoked, now smoked, smoked until pregnancies, and former smoker. However, we just want to look at 2 groups today, so we're going to collapse these into any type of smoking and the never smoked. Goodness me, never smoked. So if you know anything about the relationship between smoking and pregnancy and birth weight of babies, you'll know that just grouping any type of smoking together is not necessarily the most sensible thing to do, but we'll have a look at that next week when we look at analysis of variance. So for now, we're going to look at the birth weight and ever smoked. So for all of our tests, we're going to be using the assumptions as they've been written in the layered pages. You can find obviously the independent t-test in a lot of textbooks and other websites. They might write the assumptions slightly differently. But just for simplicity, I'm just going to use these, and I quite like the way they're written anyway. Mostly because the first 3 are around checking you've got the right type of data. And sometimes I find there are textbooks which kind of skip over the right type of data and just go straight to outliers and normality and that type of thing. So our first assumption is that our dependent variable is continuous, and it can be interval or ratios. So it could be count data if it meets the other requirements, or it can be this ratio type data. If you're not familiar with the ratio term, I wouldn't worry too much. Continuous is fine. In this case, we've got birth weights, so that is continuous. Your independent variable should be 2 categorical independent groups. So either our mothers have ever smoked or they haven't. They can't belong to both groups. We should have independence of observations, and this is down to the design of the experiment in that we have a good, strong methodology. It's not something we can usually test for statistically. There are a couple of sort of cases where we can look at some things, but usually it's a design issue and you want to justify that you've collected your data in a reasonable manner. In this case, we're just going to have to trust that all these mothers were independent of each other. Then we get on to the assumptions around the actual patterns in the data, and these are ones that we can check using graphs or tests. We want to check that there's no significant outliers. So the t-test is around testing the means as a measure of the center of the distribution. If there are really strong outliers, it might be that the mean is not the best measure of the center of the distribution, and perhaps we should be comparing medians, or perhaps we should be comparing ranks or something else. And we'll have a look at some examples of what might make an outlier significant or not as we go through the course. Our dependent variable should be approximately normal for each group of the independent variable. And the t-test is very robust. It holds up really well and it usually works. So if it's not quite normal, it's probably not going to matter. And so I don't think it's necessary really to do a formal test of normality. I think it's okay to graph your data and have a look at it. If it turns out that you've got really heavily skewed data, perhaps a lot of outliers, and it might be indicating that the mean is not the best measure of the center of the distribution, then we wouldn't use the t-test. We'd use a medians test or some other test, and that's where we would stop this process and move to a non-parametric test. The last assumption is around the homogeneity of variances, meaning that we've got a similar amount of variation in the 2 groups. If this assumption is not met, that's actually not a deal breaker. There are some variations to the test which can adjust for this. So this Levene's test of variances will get spit out automatically with the t-test, and it will give us 2 versions of the test depending on whether or not this is met. So you might like to keep that open on a second screen or have it printed out or keep some notes on it. I won't bring it up again. I'm just going to go through the analysis process. So starting off with assumption 4, which is where we start looking at the data, we're interested first in, are there any outliers? And to do that, the easiest way is to simply do a box plot. So I'm going to go down to box plot here, drag in this one that lets us split the data into groups. The y-axis is the dependent variable or the outcome of interest, which is birth weight. And we want to split it into the mothers who have ever smoked or not. So we'll drag that down there. Now, if you're in an earlier version of SPSS, you might not have this filter box here. That's okay. We're not going to use that. So just press OK. Now, I think we'll look at formatting the graphs in a separate video. This graph is not ready to cut and paste into a report, but we'll do that separately. What we're interested in at the moment is, are there any significant outliers? And in this case, we do have a lot of outliers, but they're actually what I would call fairly balanced, because outliers can sort of pull the mean, a lot like if someone heavy jumps on one end of a seesaw, they can really, I guess, pull the seesaw in their direction. If you have like a heavy person on each side of the seesaw, so maybe you have toddlers along the seesaw and one dad jumps on, he's going to have a big influence because he's an outlier compared to all the toddlers. But if a dad jumps on either side of the seesaw, then they're going to balance out and it's probably fine. So in this case, I would say I'm actually not too worried about it. And we'll move on to the next one, checking for normality. Now you can do I'm in Chart Builder. To check for normality, I would normally just have a quick look at a histogram. There are some other plots you can use. If you're getting very technical, you could look at some quantile plots, QQ or PP plots. We're not going to really do that here. I don't think it's necessary for a lot of these tests. So we're just going to do a histogram. Now you'll notice along here we've got histogram for the variable by itself, but that's not going to split it into groups. We've got a stacked histogram, which I think are just really difficult to interpret because things are on top of each other. And we can do a population pyramid, except we won't be able to use that again next week when we've got more than two groups. So what we're actually going to do is, rather than pick one of these or get into any sort of fancy commands along here, we're going to go to the legacy dialog and use this histogram. So I'm not in Chart Builder now, legacy dialog, histogram. I'll drag these in again. The variable of interest is the birth weight, and we want to split by ever smoked. You can make it show a fake normal curve on top of it. It will put this curve on top of any data you ask it to, and it doesn't mean that the data is normal. So maybe we'll leave that off for now. So we're looking to see, does it approximately show a bell-shaped curve, and is the mean a good measure of the centre? And I would say in this case it's fine. We do have some outliers here, and we could see this before in the box plot, so I'm not too worried about those. And then the last assumption is that, do we have a similar amount of variation? Now it looks fairly similar, but these are also really large samples, so it's possible that any tiny difference will get picked up by a test. But again, it's going to give us two versions of the test, so that's not a deal breaker. So I'm now ready to run the independent t-test. We're going to go to compare means and pick the independent one. We don't want a one sample and we don't want a paired. I'll just reset that again. Birth weight is our test variable. You notice these little names change on all the different things that we can do in SPSS, which is a little, I guess, frustrating when you first start using it, and after a while you stop looking so much at those labels. Our grouping variable is the ever smoked, and we have to tell it how it's been coded. So 1 and 2, I'm pretty sure. You can just go back to the data and have a look at that, or look in the variable view. If it's wrong, we'll just come back and change it. Okay. So what have we got here? Now, I was trying to find a way to make these output fonts bigger, but it was taking me ages and I couldn't work out how to do it. You can double click and bring up the an editable version of this chart and resize all the fonts there, but I can also apparently preview the data. Oops. And that makes it a little bit bigger too. So the first set of data it gives us are some summaries of the groups. 533 mothers never smoked, 678 have smoked at some point. I don't know when and where this data is from. It looks like a fairly high smoking prevalence. They're not all, doesn't mean they're all still smoking, but have ever smoked. The mean birth weight is around, I believe that's about 3.4 kilos, so 122 ounces versus 116 ounces, so there is a difference there. Is that significant? That's what we'll see in the test, and our standard deviation and standard error of the mean if we need those. So the next part of the output gives us both the test for the variances and then two versions of the t-test depending on whether or not the variances are equal. So I'll just, that's probably big enough. So Levine's test for equality of variances. The null hypothesis is that the variances are equal. We have good evidence against that, and therefore we'll assume that the variances are not equal. So we'll use the second row along here. T-test for equality of means. So this is our test statistic here under the t-value, our degrees of freedom, and our significance, which is our p-value. And we're looking at the second row, equal variance is not assumed. The null hypothesis is that the means are equal. We've got very strong evidence against that null hypothesis, and therefore we would conclude that the birth weight of babies born to mothers who have ever smoked versus never smoked is different. And we don't stop there. We don't just say, yes, there is a difference. We have to explain what that difference is. And this is where we get the confidence interval for the difference. So it says that the mean difference is about 5.8 ounces with a confidence interval from 3.7 to 7.9, or 3.8, I'm not rounding very well, to 7.9. So we do need to include a measure of how big this effect of smoking is. So I'm just going to close that view. It's split the test into 3 rows doing that, but you'll see that that's written all across in one row here. So we have the variances test, the t-test, and then some information about the difference. Now the last thing that I would like to do, even though we've run the test and essentially got our answer, is to make sure that we can do a graph of these results. And what we're interested in now is not every single observation, which we had with the box plot and the histogram. We're interested in the means and we're interested in the confidence intervals. So we're going to do what's called an error bar chart or an error plot. I can't remember exactly what it's called here. Chart builder. And it's under bar. The error bar is referring to the bar which represents the error. It's not to do with a bar chart. I actually really don't like means displayed on bar charts. I think it's confusing. I think let's just save bar charts for categorical data. So we would do this in the same way as the box plot. Our birth weight goes on the y-axis and we're going to split into our groups. And you can see over here we're doing confidence intervals. Depending on what discipline you are in, it could be standard practice to either use confidence intervals, the standard error of the mean, or the standard deviation. I prefer confidence intervals. You might be in a discipline which requires you to do a different type of error bar. So now on my graph, I actually have a line there at 120 ounces, so I can clearly see that my two means are different, but I know that in the previous version of SPSS, you won't have any lines across it, and so it's actually a little bit difficult to see what's going on. Now, if a graph is difficult to interpret, then it's probably not helpful and there's no point including it. So we need to think about how can we make this graph easier to understand. And I think, although I said I'd look at manipulating graphs in another video, and I will do a separate video on it, I just want to change the scale here so we can actually see what's going on. So I'm going to double click into the graph and then click on the y-axis. I'm going to double click, sorry. And whatever it's letting you edit will show up with a yellow outline. And in this case, I want to change the scale. It's going from 0 to 125. I'm going to bring that up to 100. And it just has the effect of zooming in so we can see these means and confidence intervals better. So this is not all the data. It's not the same as a box plot which shows all the observations together. It's just showing the means and the confidence intervals. And there's absolutely no overlap between the confidence intervals. And this is why we've got a significant result. So this is strong evidence of a difference between the means. If there's a little bit of overlap with the confidence intervals, you may still get a significant result due to some quirks in the way the maths works out. So if the confidence intervals don't overlap at all, you definitely will get a significant result. If they overlap a tiny bit, you might still get a significant difference. If they overlap a lot, then you probably won't. So I'm going to close that off here. In the next video, we'll look at doing a non-parametric test for the medians if the mean is not a sensible thing to test. And then at some point I'll do a separate video of how to format graphs nicely, but I might save that for a bit later until we actually need to use it for posters or reports.